Well, if that was Click, I guess I'm Clack. I'm Cliff Konold from the Scientific Reasoning Research Institute at the University of Massachusetts Amherst. So along with the arrival of big data, which we've heard about, we've witnessed also an explosion of graphical types and designed supposedly to harness the native abilities of our visual systems. Let me test this. Which one don't I hit? However, what constrains our ability to extract information from data displays, I don't think is optic nerve bandwidth. Research, in fact, indicates that what we perceive in such displays is dependent in large part on our conception of data, and in particular on our understanding of variability. Here's a relatively simple display showing the weights of two types of fish. We asked both statisticians and novices to judge from this graph whether one type weighed more than the other. And we displayed graphs like this on a computer using a restricted view methodology that allowed us to also record how they visually scanned these graphs to make that decision. Here's a typical novice scan path, up and down across the two distributions. Novices appeared to be trying to find a diagnostic cross-section which they used to compare the number of cases from each group. Experts, by contrast, tended to scan horizontally across each distribution, one group at a time. And we believe they were trying to locate the centers of each distribution and then compare the relative location of those centers. In both cases, underlying conceptions of data drove the inspection of graphs. And underpinning the expert's approach is a view of data as containing a signal that is fuzzed by variability, but fuzzed in characteristic ways. So we've been designing environments to introduce and nurture the idea of data as signal and noise. And at the heart of that perception is the idea of modeling. So we'll look at three examples of the types of modeling tools and contexts that we've been developing. And I've got an hour, right? So we were exploring with a group of fourth graders why cattails might vary in length. And as a group, we developed this list of factors that might influence tail length. And then we created a model with real spinners, but that I've implemented here in TinkerPlots, our data analysis and modeling tool. So a value is randomly drawn for each factor, and these values are then added together to give a tail length. Before running the model, we asked students what kinds of results they'd expect. They initially thought that they'd get an even distribution of results across the possible range. But after simulating only a few tails, they realized that they'd get more middling lengths because in their words, you'd have to be real lucky to get a very long tail or very unlucky to get a short tail. So one important idea here is that independent sources of random variability tend to cancel one another, thus allowing the signal to become more evident as the sample grows larger. This graph shows the weight of 400 pumpkins. The group on the top were fertilized, the group on the bottom were not. Of course, the question is, did the fertilizer have an effect? This is a problem we've given to 8th graders once they've become comfortable using means or averages to compare groups. And in TinkerPlots, they can snap the ends of a ruler on to read off that difference. But then we reveal that these are virtual pumpkins grown in this sampler. So a pumpkin first gets a weight from this reference distribution and then is fertilized or not, and then gets some unknown additional weight. And the question is, what's in that fertilized box? After repeated sampling, students make a guess, after which we can reveal the hidden value. Here, a signal is an additive shift of one distribution relative to another. With Bill Finzer and his colleagues, we've been exploring more recently the use of computer games to foster learning in math and statistics. Ship Odyssey involves the context of repeated measure, a context where we believe the idea of signal as true measure and noise as measurement error is perhaps the most salient. To locate treasure, you send trained rats down to the ocean floor, here 5 at a time. But the location readings that the rats give are noisy. So how do you make use of those noisy data? How many rat readings do you need to set the location of this hook to reliably capture that treasure? This game motivates the need to measure variability and helps develop a sense of the relation between a sample size and the sample variability of its mean. We view our technology tools as giving students access to a new, powerful way of modeling using what Jim Caput called dynamic notations. Using this form, students not only construct a model of a situation, but run it and tweak it and watch results accumulate in real time. They come to view graphs of data as process output, where small changes in the process become evident as the sample grows. So these are the perspectives we believe our students need in order to make sense of and draw insights from the graphical displays they now see all around them. So thank you very much.